Morning.
Good morning.
We'll wait a minute, 1 minute. I know it's Thursday, but we'll wait for a couple of minutes. Go ahead and share my screen. Hopefully you got a chance to pull a handout. Let's see. Come on. There. One second. All right. So we left off talking about light and frequency and wavelength. And one of the things we talked about was how the wavelength and the frequency are inversely proportional. So, and I'm gonna show that on the next page. We start talking about the energy of light and the energy of a photon. But so the wavelength is the distance between peaks of a wave, and the frequency is the number of times that particular peak passes a point. So that's why it's measured in hertz or reciprocal seconds, and then wavelength is actually measured in nanometers because it is a distance. So on the table here, which is in the handout, this is the visible spectrum. So this is the light that we can actually see. So this is kind of situated between the infrared spectrum and the UV spectrum. So the infrared is just a little less energetic or lower in energy than the red region. And then the ultraviolet is a little higher in energy than the violet region. So you can see here, this is the spectrum that you learned in grade school, right? Roy G. Bill, if you remember that. Right, those are the colors of the spectrum. So red, orange, yellow, green, blue, indigo, and violet. And what you'll notice is, let's look at the difference in the frequency and the wavelength. So the frequency here is 8,000, and the wavelength is, the wavelength is 8,000 angstroms, and the frequency is 3.7 hertz. And the energy is 2.5 times 10 to the minus 19. We're going to talk about that shortly. Joules. And if you go up to orange, you can see the wavelength gets shorter and the frequency goes up. So does the energy. Same here in the yellow region, the energy, the wavelength shortens, the frequency increases, and the energy increases. And so you can see that energy increases in this direction. So energy is increasing from red up through violet. And for the visible region, you can see that violet or purple light is the highest in energy, right? And that's all based on the wavelength as well as the frequency of that light, right? So let's talk about how we can calculate the energy of light, because light is kind of thought about in two different ways. There's really what we call the particle wave duality of light. What that means is that light can behave both as a particle or as a wave, right? It has characteristics of both. And so when we think about light and its energy, the way that we calculate the energy is to think about both of these characteristics in the sense of light behaving as a particle, meaning that we can calculate the amount of energy for one particle, but also light behaving as a wave, and that we can use either the wavelength or the frequency to calculate that energy. All right, so there are two schools of thought here. Under the classical mechanics school of thought, is believe that matter can have any amount of energy, but quantum mechanics, again, we're not going to go into all the details about that, because that's more physics and physical chemistry than CHEM. But one of the key concepts of quantum mechanics is that energy is transferred in quantized amounts or discrete amounts. And so using that idea, we're able to calculate the energy of what we call a photon of light or a packet of light, right? So one particle or packet of light, we call it a photon. Again, drawing on the particle wave duality of light. So one particle of light is called a photon, and the energy of that particle or that packet we can calculate using this equation. All right, so this is the energy of a photon, which is a quantizable packet of light. We can calculate the energy using the equation shown here. The energy of a photon is h times nu, right? Where h is Planck's constant, and then where nu is the frequency. All right, and the energy of a photon is going to be calculated in joules, because Planck's constant, again, another number you'll never have to calculate because it is a constant. Planck's constant is 6.63 times 10 to the minus 34 joule seconds. So when you look at the table, you can see that these numbers are in joules, right? You see it's 10 to the minus 19 joules, and then you see right here the frequency is 10 to the 14th hertz. So you can see how that cancels out if you multiply 10 to the 14th, a number, or 3.7 times 10 to the 14th by Planck's constant, which is 6.63 times 10 to the minus 34. You can see how the exponents are going to cancel and give you that number. You can see right here is measured in as 10 to the minus 19. So we're going to work through a few examples of that to calculate the energy of a photon. It's very straightforward. And so when we think about the different colors that we see with our eyes, some of us may have some issues being colorblind, nearsighted, farsighted, whatever, but the colors that we see are based upon the fact that the cones and rods within our eye pick up on the different parts of the spectrum based on their energies, right? So the colors are based on the energy of the radiation, because all light is electromagnetic radiation. It has an electronic component or electric field, and it has a magnetic field component. And then the UV energy being slightly higher than the violet region, that UV radiation is the most dangerous to us because UV energy is enough to cause bond cleavage, right? Covalent bond cleavage. So if you have and let me show you that. If you have a covalent bond, let's say between two carbons. So let's say this is a CH3 and this is a CH3. If you shine UV light on this, right, you can actually break off one of those hydrogens. Usually it's done with an initiator, but I'm just showing it. Right, both of these are what we call, and you've heard this term before, free radicals. So UV radiation, it is energetic enough that you can form free radicals because you can actually break bonds, right? This is this type of bond breaking where you split the bond in half and each atom takes one electron. We call that homolysis. Right, so this is one of the reasons why it's important that when you're in the sun, you wear sunblock. That's one of the things that sunblock does is it slows this process down by blocking out UV radiation from the skin. But if you notice, like even if you're in the sun for any period of time, you can notice even that your skin is going to darken up some. Sometimes you might develop like spots or freckles or whatever. All of that is because the chemicals in the skin are reacting with, or not reacting with, but are altered by that UV radiation. All right, so we talked about the energy of a photon. Let me put that down here because I want to show you something else with this equation. All right, so we said E is equal to H nu, where nu is the frequency. But let's say we have let's say we have we don't have a frequency. Let's say we only have a wavelength. Well, remember that the speed of light right is the frequency times its wavelength, right? And that's, let me fix that, that's lambda. So it's nu times lambda, right? This is the frequency and the c is the speed of light. Nu is the frequency of the light.
Recording.
And this is the wavelength, right? So we can also think about how to rearrange this relationship so that if we don't have a frequency, but we only have a wavelength, we can still figure out what the energy of a photon is, because C over lambda equals the frequency, right? And so the speed of light being measured in meters per second, right? It's just it's a very simple calculation to get the wavelength into meters, because if a wavelength is measured in nanometers, we can just convert that into meters by taking the nano part and turning it into the exponent. And I'll show you that in a second. So you can always think about this also as the energy of a photon is, it can be H nu, or it can be H times C over lambda. Come on, Russell. Right, you can always sub in the C over lambda for the frequency. All right, so let's say we have light. Let's say what's the energy of a photon with a, let's see, 900 nanometer wavelength. Right, so energy of photon with a wavelength of 900 nanometers. So we can figure that out if we say that energy is h nu, but here we don't have a frequency. So we're going to sub in that relationship between the frequency and the wavelength, h times c over lambda. And we know h, 6.63 times 10 to the minus 34 joule seconds. We're going to put that number in, and then we'll put in c, 3.0 times 10 to the 8 meters per second. So you can already see the meters, I'm sorry, the seconds are going to cancel out here over lambda, which in this case is 900 nanometers, but we need this to be in meters. So let's do a quick conversion. 900 nanometers times 1 meter. I'm sorry. 1 times 10 to the -9 meters over 1 nanometer. Right, so we can cancel out nanometers, and we can see that this is 900 times 10 to the -9 meters. We're not going to worry about the scientific notation, although if we move that decimal back, it's going to be 9 times 10 to the 11 meters. But we're not going to worry about that. We could just keep that number how it is. We'll just put that in. So meters are canceled. So meters here are going to cancel. Seconds are going to cancel here, and the answer is going to be in joules. All right. So let's see if we can get that calculated real quick. Let's see if I can. So 6.63. Where's my exponent? Hold up. 6. Okay, all right, so I have the energy being 2.21 times 10 to the minus 19 joules. Right? Anybody have a question about that or not? Or was anybody not able to to calculate that? Right, and again, it's really
only because I don't have my scientific calculator, so I wasn't able to do the little exponent part as fast. But yeah,
okay. Yeah. Okay, that's okay. So, but the point is, if we don't have the frequency, we can always use the wavelength. We have a wavelength. The speed of light is a constant, and Planck's constant is a constant. So we have a wavelength. We can figure this out because we can just use a different expression. We can substitute in c over lambda for nu and solve it that way. And our wavelength is more than likely is going to be measured in nanometers. So we always have to convert that into meters. So that's the other important thing here. Everything else is it's all academic. But the reason you want it in meters is so you can cancel, right? Because the speed of light is measured in meters per second. So you want to be able to cancel out meters, and then you want to be able to cancel out seconds with the Planck's constant, which is in joule seconds. So you can get joules as the energy unit. All right. Any questions about that? That's really the extent of the energy of a photon. It's just a matter of knowing how to manipulate between frequency and wavelength. That's the hardest part. And if you know the relationship between the frequency and the wavelength, and that it's inversely proportional with the speed of light, then you can't miss. All right. Any questions about that? All right. Let's go to the next section, still dealing with light and photons. And one of the ways we know that photons exist is by the observation of what we call the photoelectric effect. And that's just taking a metal surface and shining light on it and being able to eject electrons from that surface. And we talked about this before when we talked about the cathode ray earlier, way back when we first started talking about the structure of an atom and what the cathode ray was actually made up of electrons, but the electrons were coming from a metal, right? Because they were being irradiated, the metal was being irradiated, and then there were electrons coming from it. So what the photoelectric effect is the ejection of electrons from a metal surface when you expose it to electromagnetic radiation. And the only way that you can make an electron move is that the radiation has to have a higher frequency than the threshold frequency for the metal, right? And that makes sense. And this brings up another point, because when we think about the photoelectric effect and we think about like moving electrons from a metal, the thing to remember, which we're going to talk about in a second, is that these are always going to be your outer shell electrons. So your valence electrons. So when you're able to eject electrons from any substance, any element or atom, when you're ejecting electrons, normally it's going to be those outer shell, those valence electrons that are furthest away from the nucleus. But when we think about this, it also brings up another point. And the point is that when you have an atomic spectrum, right, for a given atom, right, you have different lines in that spectrum because you have different energy levels of electrons, right? So electrons are in the metal, they're surrounding the nucleus, but they're in different what we call shells, which I'm going to show you in a minute. And those electrons can get excited, but normally it's the excitation usually happens between two levels in the outermost region of the atom, right? It's very difficult to excite an electron that's close to the nucleus. So every atom can only emit certain frequencies, and that's because every atom has different energy levels where those electrons exist. And when you have a element or an atom that emits a photon, that's what that happens when you excite an electron up one level and then it drops back down in energy. So you can excite it, and then when it drops back down, it releases energy, and that energy is in the form of a photon. It's like a transition between two energy levels, right? So let's talk about that in terms of electron configuration, right? That's a great segue into that. Thinking about the energy levels in an atom, in a given atom, and where the electrons are located and how many electrons are present in that atom. it brings us to this point where we can talk about the configuration, the electron configuration. And you've probably seen this when you took high school chemistry, the Aufbau buildup, where the energy levels are here, right? So the numbers are indicative of the energy levels, right? And you know, you have all the way up to level 7, right? But those are for huge, those big lanthanides and actinides that are on the periodic table that have a lot of electrons. But the energy levels are illustrated by this buildup. And I'm gonna show you this in more than one way. So you can see right here, in the first energy level, that's only the 1s orbital. And so let me back up. The letters here are, these are your orbitals. And I'll show you those on the next page. Right. So in the first energy level, it's only 1s. And then the second energy level, you have, notice, 2s and 2p. The third energy level, 3s, 3p, and 3d. And the fourth energy level, 4s, 4p, 4d, 4f, like that. So as you increase in energy, you also increase the number of electrons that are stored up in that particular energy level. And we're gonna talk about the number of electrons each orbital can hold and all that stuff. So with that being said, when we think about the electron configuration, we think about how many electrons can be in one orbital. So any given orbital, whether it's S, P, D, or F, because there are 4 orbital types. Right, there's the S orbital, there's the P orbital, there's the D orbital, and there's an F orbital. Let me say this too, for because I can say the word orbital all day. The orbital itself is a graph. It's not real, right? You can't touch it. It's not tangible. It's a graph of the equation of the path of an electron. Right? So an orbital is a graph of the equation of the path of an electron around the nucleus. So you got basically 4 different types of orbitals, S, P, D, and F, and they all have different shapes because they are graphs of an equation, right? So they got different shapes and they're all along different axes, because when you think about graphing an equation, you have 3 axes. You have the X, the Y, and the Z axis. And so I'm gonna show you that in a second. But as far as like the electron configuration, the energy levels are broken down this way, right? So you have 1s, and then in the second energy level, 2s and 2p, third energy level, 3s, 3p, 3d, and so on and so forth, right? And we're going to talk about the quantum numbers and all that stuff in a second, but I just want to show you like the buildup, because the way I learned it was like this, linear, right? And that takes, it doesn't take into account, like I could stack these, like I have them stacked here with the red arrows going through them. It's a little bit easier to think about when they're stacked on top of each other like that, right? Because now you can see I got 7 energy levels, and then the first is 1s, second one is 2s and 2p, third one is 3s, 3p, 3d, like that. and when you do it that way, you see that the similarity between 4, 5, and then also between 6 and 7, or 6 and 3. See how 3 is 3s, 3p, 3d, and 6 is 6s, 6p, 6d, and then 2 and 7, similar, very similar. So when you see it that way, it makes it a lot easier to think about how to remember what the energy levels are. And we're going to talk about that shortly, because it also is going to help us with building up electron configurations for specific atoms or elements. All right. So you look at, this is just another way to look at it. I thought this was a pretty cool illustration as well, right? And notice the number N, we're going to talk about it, but I can introduce you to it now. N is what you call the principal quantum number. Right, that letter N indicates the energy level. Right, and as you go this way, energy is increasing. Right, questions? Any questions so far? So how do we get to this point? Well, we were talking about photoelectric effect. We're talking about exciting electrons and moving them and transitioning them between energy levels. So now we're talking about what the actual energy levels look like. And that connects to the atom, and that the electrons that are around the nucleus are in these different energy levels. And we can build a configuration for any atom as long as we know its atomic number. Because remember, way back second, third week, the atomic number is indicative of how many electrons are present and protons, right? So the atomic number is electrons and protons. The atomic mass is mostly the protons and the neutrons that are in the nucleus that make up most of the mass, right? But because the electrons are negligible when it comes to determining the mass of an element or atom, right? So these are the different orbital shapes, right? Again, these are graphs. So that's why the axes are shown. The X, Y, and Z axes are shown. Notice for S, it's just a sphere, right? It's not in 3D, but it's actually a 3D. It's a spherical shape. And then for the P, you actually have 3 P orbitals, PX, PY, and PZ. And you see here, PX is here along the X-axis. I should have used a different color. Right? PY is along the Y-axis. And then PZ is here on the Z-axis. The two. So that lobe, let me give you a little bit more insight on the P orbital. So the P orbital is shaped like what we call a dumbbell. And depending on what axis it's on, it's going to have a positive side and a negative side. I'm just prepping you for organic, by the way, because that's what I teach. So I'm always going to talk a little bit more about that part. Between the two lobes in the center is what we call a node. No electrons can be there. So that place is devoid of electrons. It's actually where the graph passes through 0. So it's a place where the graph passes through 0. So no electrons can be in at that particular location, but they can be in the top or in the bottom. And the plus and minus is not a charge. It's actually the sign of the equation. Right. So depending on what side of the axis it's on, if it's on the positive side or the negative side, the sign of the equation is going to either be plus or minus. All right. So that's the P. There are 3 P orbitals, and then there are 5 D orbitals. You can see that you have, I think it's DXY, DXZ, DZ squared, DX squared minus Y squared, and then I think it's dy squared. The orbitals are not listed here, but they have like different notations. And so with the d orbitals, you can see that they are kind of shaped like a clover leaf, right? You don't really encounter d orbitals until you get to like your transition metals and some of your metalloids. Like silicon has d orbitals, if I'm not mistaken. Phosphorus has some d orbitals. So it just depends on like what atoms you're dealing with. But all of your transition metals, you're going to encounter some d orbitals, and that's actually how they do their chemistry. The d orbitals are, some of them are vacant, and they can accept a pair of electrons, and so a lot of your transition metals form complexes with non-metals like nitrogen or carbon or phosphorus or different or oxygen or different atoms like that that can grab onto that metal through a process what we call chelation. And I'm not even going to get into the F's because you won't ever see these unless you are working with some like high level lanthanides and actinides using them for catalysts or something like that. You won't see the F orbitals. So I'm not going to read, but I will say that there are 7 F orbitals. All right. So here let's talk about something else that we can discuss, and I can give you some insight on. So each orbital is capable of holding 2 electrons. Right. Now I want you to notice a couple of things. Number one, so each orbital can hold 2 electrons. That's any orbital, right? What I want you to notice for the electrons is a couple of things. Number one, I put them in the same orbital, but also I want you to notice that they're what we call paired up. So one of them has a spin that's up, right? And one has a spin that's down, right? So the electrons are paired up like that. They're always paired up with the opposite spin. That's on purpose. And the reason is because if they have the same spin, then it violates one of our rules, which is the Pauli exclusion principle, which we're going to talk about in a second. So you pair them up, spin down, right? And if you have, let's say for the P, where we have actually 3 different p orbitals. So px, py, and pz. You can have a total of 6 electrons, right? And when you put the electrons in here, the p's, right? If I don't have any energy levels denoted, these are what we call degenerate orbitals. Right? What that means is that they all have the same energy. Right? So when I fill the P's, I have to put 1 in each P before I put 2 in any. Right? So let's say I only have 3 P electrons. Well, I'm not going to put 2 in PX and then put 1 in PY and leave PZ empty. I'm going to evenly distribute those electrons until I run out of them. Because in degenerate orbitals, Hund's rule says I have to put 1 in each before I put 2 in any. That's how easy way to remember that. 1 in each before 2 in any, if they are degenerate. So then when I come back to put in the other electrons, I'm going to fill it like so. Right? So the p orbitals, the 3 p's can hold up to 6 electrons total. Right? Because every orbital can hold 2 electrons. Since there are 5 D's, no, make those a little smaller, sorry. Right, so I'm just gonna say dx, dy, and dz, and then dx squared minus y squared and dz squared. Those are the d orbitals, and then the dz squared is this one, if I'm not mistaken. It's like what we call a dumbbell and a donut. So you have like a kind of a P-shaped dumbbell and then a donut or circular piece around it. So yeah, so we do the D's. We put one in each. These are also degenerate. So we'll put one in each, but then it can hold up to 10 electrons. All right, so then I can put the next set of electrons in like so. And again, they have to be paired up differently. You're not going to put in 2 electrons with the same spin because they're going to repel each other. So you want them to have opposite spins when they're in the same orbital. So that's why we draw it like this. Some notations you'll see it with like a full arrow. That's fine too. I just like the half arrows because it looks cooler to me. But you can put in a full arrow, it doesn't matter. And it's the same thing for the F's. You got 7 F orbitals. And each one of them can hold 2 electrons. Right, so the F can hold a total of 14 electrons. So S can hold 2. The 3 P's all together combined can hold 6. The 5 D's combined can hold 10. And then the F's can hold 14. And when we think about all this, what all this stuff means, we're going to come back. We'll come back and talk about the quantum numbers on Friday. We'll do the quantum numbers and we'll do some examples of electron configuration. I want to start that right at this moment because I'm going to get lost in the sauce and then it'll be 11 o'clock. So I'm going to stop here. Are there any questions about anything? Like a lot of this stuff is more theoretical, but the electron configurations do matter because when you think about how chemical reactions happen, especially between non-metals, the only reason they happen is because of how the electrons are configured in certain atoms. So we're going to talk about this. We'll finish this up on Friday. And then on Monday, we'll do Lewis structures and we're going to be done. That'll be the extent of this class. So any questions? All right. If not, I'll see you back on tomorrow. Okay, I see your message.
The last stuff that we've been doing for the last like week, it's not going to be on the exam, right?
Well, we're going to talk about that on Friday. We'll talk about it on Friday because I'm really trying to figure out, like, let me stop recording. I don't want to give all my trade secrets away. But I'm really trying to figure out, like,